have 4 lightning talks from active PhD students in CRU. And so they each have 5 minutes. They'll need to speak with this microphone. The first speaker is actually online, so it won't apply to her. And then we'll have questions and answers at the end, okay? So 5-minute lightning talks. And so without further ado then, we'll move on to the first speaker who's online. Is she there? Yeah, good, okay. And so it's Nele Reyniers, and she's looking at drought in the UK, and she's actually sponsored by Anglian Water. Over to you, you have 5 minutes.
Hi, I'm Nele, currently in the 3rd year of my PhD at CRU, and I'll be talking about some of my work on modeling future droughts in East Anglia and the different sources of uncertainty that we see along the way. Okay. So the UK has experienced quite a few droughts in the past and also in the more recent past, and what is shown here. And these droughts have had impacts across different sectors as well as on the environment. So it's quite important that we understand how they evolve towards the future. Moreover, the map on the top right of the slide is a reminder of the range of climatic regimes that we find across the UK. It's not just as humid everywhere, it's almost an order of magnitude difference between the wettest and driest place. And if we then zoom in on one of the driest regions, the east of England, we can refer to past piece of work, also in collaboration between CRU and Anglian Water, characterizing how these past droughts have manifested in the east of England. But that's the past. What about the future? From the UKCP18 projections, we know that we can expect hotter and drier summers, warmer and wetter winters, depending on the degree of climate change. These seasonal cycles zoom in on the east of England and show this enhanced potential evapotranspiration and its seasonal cycle, as well as slight drying and precipitation in summer. That's a climatic average. What about drought events? So next, I compared projected changes in extreme drought frequency between 2 drought indicators that only care about atmospheric variables that directly come from the UKCP18 regional climate simulations. And the difference between the projections on the top row and the bottom row is that the top row cares only about precipitation. There's no evaporation happening. On the bottom row, we care about precipitation as well as potential evapotranspiration, which is the drying power of the atmosphere. And we don't take into account that sometimes there's no moisture to evaporate. So you can see there's quite a significant difference between these projections based on these 2 quite often used indicators of drought. So that's a significant source of uncertainty. But if we now want to know what's going to happen to streamflow droughts, in particular catchments or across the grid, we're going to have to turn to other models to assess those projected changes. And so we can drive hydrological rainfall runoff models with the output of climate models that may have been dynamically or statistically downscaled. And typically we'll first do some statistical correction to ensure that the streamflow projections are sensible. And then from that streamflow we can define droughts. Each link in this impact modeling chain is bringing in some uncertainty, which we can sample at least. So for example, in my approach, I'm using 4 hydrological model structures, each with many parameter sets, and each of those combinations is driven by each of the ensemble members of UKCP18 climate projections. And this leads to something like this, a large ensemble of possible projections of stream flow drought frequency. This is results, preliminary results for the WENSM. And then the next steps are going to be to quantify and attempt to reduce that uncertainty. So how important is a hydrological model choice compared to the climate model range? And can we try to gain confidence in these projections by appropriate model evaluation approaches? I think that's probably my time. So thank you very much.
Thank you very much. Perfect, perfect timing there. So we'll move on now to our second speaker. Qianyu is going to be talking about the flooding in the UK. Right, so where are the talks?
Next slide.
Okay. Right, okay, over to you, 5 minutes.
Hi, happy to see many of you here. I'm Qianyu, a third-year PhD student, and my talk today is entitled Future Changes of Flood Events in the UK Under Climate Change. And I look at the flood risks in the UK in future by using the hydrological model. So before the hydrological simulation, for the input data set here, I use UKCP 18. It is known to consist of large systematic difference between the model output and the observations. So the bias correction is the first step. Here, the quantile mapping bias correction method has been used. I did the bias correction for precipitation and temperature in each month separately. So the evaluation of the results was compared from the monthly value. So here is the result. We can see it's the comparison between the observation and bias corrected monthly precipitation and temperature. The blue line is the raw UKCP 18 ensemble mean. Yellow line is the bias corrected ensemble mean. And the black line is the observations. We can see it's obvious after the bias correction. The yellow line and black line basically overlap, especially in temperature. And then we can move on to the hydrological simulation. We have HBV hydrological model, CAMOS GB catchments, including 671 catchments in Great Britain, and we have 28 catchments in Northern Ireland. This figure on the left shows that the model performance for all catchments in the UK over the baseline historical period, 1918 to 2010, 30 years in total. And we use the Nash Sutcliffe efficiency to see the model performance. We can say the left figure, the model performs well for much of the UK. However, the NAS value is in southeast catchments of England is low. After removing those catchments, we got the figure on the right. So there are 77% catchments, a NAS value over 0.6. And then we do the hydrological simulation. This is the future changes. We did this with contribution from Desmond Manford and my colleague Nicole and my supervisor Helen He. Two of them are funded by the OpenClim, and this project led by the Professor Robo Nicholas, and this project is designed to support UK assessment of climate risks and assessment. And we move back. This figure is the projected change of 95th percentile, which is high flow, and mean flow, and the 5th percentile, which is low flow, between the baseline period and the future period. The future period we use is 2040 to 2070, and in total 30 years as well. From the figure on the top, we can see that there are some big increases in high flow, especially in western and southern coastal areas in GB, and there are some decreases in east coast, and we can find the figure on the bottom, and it's very obvious it's red, so the decreases in low flow. But I look at the flood risks, so I also calculate the chances of discharge in 100-year return period in both historical period and the future. And we can find that the increases are particularly apparent in western and southern coastal area in Great Britain, and decreases are most visible in southeast area. And my next step is look at the overlay, move on to the overlay data set, and to do the overlay hydrological simulation, and then do the assessment of flood risks in the UK as well. So that's it. Thank you.
Well, thank you very much. And again, thank you for keeping to time so well. So our next speaker now is Sarah Berk, and she's going to be speaking about climate change in an urban context.
Okay, hi everyone, can you hear me all okay? So today I'm going to be talking about my research, which is to do with the urban heat island effect. So cities are typically warmer than the surrounding rural area, and this is something that we know as the urban heat island effect. And it's essentially defined as the difference in temperature created by the presence of a city. So this schematic here shows some of the main causes of why the urban heat island exists. So these can be due to factors associated with the built environment. So anthropogenic heat and city geometry trapping heat within the city area. And then there's climatic-based factors. So an example here is rainwater being stored in soil and vegetation, and evapotranspiration. So this is really important because when there's a lot of moisture available, the solar radiation is absorbed by the change of state from a water to a gas rather than actually heating up the environment. So for my research, I'm using satellite data. So I'm looking at the land surface temperature. So this is why I'm calling this the surface urban heat island, to distinguish it from the air urban heat island, which is the 2-meter air temperature. So the plot above here is the annual average surface urban heat island for some of the cities that I'm looking at. And something that you'll notice here is that the heat island is strongly positive in some areas and it's strongly negative in others. And this is something which is related to climate. So the plot below shows the annual mean evaporative fraction. And this is a property related to soil dryness. So when it's low, it means that the area is very dry. And when it's high, it's a more humid area. Another factor which is associated with the urban heat island is the enhanced vegetation index, and this is a measure of abundance and greenness of vegetation. So looking at the plot below and comparing it with our surface urban heat island, you can see in areas where there's a lot of green vegetation, there's this strong positive heat island, and in areas which have desert or bare areas surrounding the city, the heat island is this strong negative heat island. So understanding what's going to happen with the heat island in the future is really important for kind of two key reasons. And the first one of these is migration to cities. So people migrate into cities in order to increase economic prospects. So by 2050, 70% of the population will be in cities. The other important factor is that we're expecting to see an increased number of extreme heat events due to climate change. So the hazards in cities are greater and they're affecting increasingly higher numbers of people. So the issue with using global climate models to look at the surface urban heat island is that the resolution is quite coarse. So, for example, 10 kilometres, whereas cities are often a lot smaller than this. There's a possibility of using regional climate models, but these are computationally very expensive. So it's hard to look at multiple cities using this, and you kind of have to focus on the individual level. So what we're working on is developing statistical models in order to predict the surface urban heat island. And we're using variables such as those two that we've just seen in order to do this. These two plots here shows the performance of one of the models. So on the x-axis is the observations made, and on the y-axis is the model prediction. So you can see that this model is doing a pretty good job. And because we're using this satellite data, the resolution is a kilometre. So the next step of my PhD project is to kind of use these models then to see what might happen in the future to the surface urban heat island. So to wrap up, what we've just seen now is that the urban heat island intensity can be both positive and negative, and this is something that's dependent on climate. We've constructed these models based on satellite data, and these can capture the surface urban heat island in both of these different climate regimes. And this has implications for climate change because variables such as evaporative fraction and the amount of vegetation in areas is going to change in the future. So thank you very much for listening, and I hope you enjoyed that.
Well, thank you very much again, and perfect timing. So, I mean, I think our sort of PhD training is sort of coming through here with everybody keeping to time very well. So our last speaker is Sophie Wilkinson, who's going to be speaking about machine learning and understanding extremes.
Okay, good morning everyone. My name's Sophie. I'm a third-year PhD student here at UEA, and I'm talking today about applications of machine learning for studying extreme weather events and how they're going to be influenced by climate change in the future. So to start off with, what is machine learning? Machine learning is a branch of artificial intelligence that allows you to train models that learn patterns from data. And the advantage of this approach is that the model requires little context-specific programming. And these models are increasingly being used in climate science as a complement to the existing climate models. So the machine learning model itself is essentially just a mathematical formula. It takes your predictor variables as inputs and outputs a prediction for your target variable. And this model formula contains coefficients, which are parameter values, which get tuned during a training process so that your model will be able to make accurate predictions. So I'm using a supervised learning training process to allow the model to learn these correct coefficient values. And essentially the steps of this process, it's an iterative training process, so input variables are passed into the model and a prediction is made based on the current values of the model parameters. And at the very beginning, these are just initialized with small random values. Then the error in that current prediction is quantified by the cost function, and then that error is distributed back through the model to these tunable parameters, and a small adjustment is made to each one, which would push the model's prediction in the right direction. This process is repeated for every training case in the training dataset, and the cumulative effect of this iterative process allows the model to learn a strong relationship, hopefully anyway, between your input and output variables. So the type of machine learning model that I'm using is a ridge regression model. This is a variation of a simple linear regression, but the cost function additionally penalizes the total coefficient magnitude, which helps to prevent overfitting, which is really important when you're interested in extreme events where you're expecting that your model is going to have to extrapolate beyond the data that it has seen before in the past. This can approximate nonlinearity in high dimensions. It's computationally cheap, so I can train it at a single location in a few seconds, and it's relatively simple and interpretable compared to other more sort of black box type models. So the model that I have trained is trained to predict daily temperature anomalies to the seasonal cycle from a selection of thermodynamic input variables. So taking a look at the local performance at a grid cell over the UK here, This is just an example test year from the data set, so summertime in 2019. The blue line is the ERA5 reanalysis, or essentially the observations, and the orange line are the predictions from the ridge regression model, and you can see that it's doing really well here. So it's capturing the day-to-day variation really well and the peaks and troughs. Zooming out to sort of a regional scale, looking at Northern Europe and Western Central Europe, the colours are the same as the previous slide, and it's a similar story here as well. The day-to-day variation on this regional scale is well captured. So what are the applications of such a model? So at the moment, I'm kind of looking at two different pathways with this. The first is looking at historical extreme events and trying to interpret what the drivers of those events could have been. And the second is to use the model for future projection and construct an observational constraint on existing climate projections. So just to demonstrate the performance of the model on an extreme event, this is looking at data from the Pacific Northwest, the region highlighted on the map in the bottom left corner, the heat wave that occurred there last year in the summer of 2021. So we have the ERA5 reanalysis data, or the observations, in blue, the ridge prediction in orange. And you can see at the end of June, there's this really high peak in temperature with an anomaly of sort of 12 degrees above the temperatures that would have been expected at that location at that time of year. And the model is able to accurately capture that. And the aim with interpreting the drivers of this event would then be to look inside that model, which variables are most important to allow it to make this prediction and kind of infer what the drivers of this kind of event could be. The second application that I talked about was constraint to future warming. So we can take the model that has learnt from historical observations and provide it with inputs from the future scenarios of existing climate models to allow it to make predictions for the future. So focusing on the panel on the right-hand side, the blue circles show the projections of the mean summer temperature change by the end of the century from the latest generation of climate models. And then the orange distribution on the right-hand side is an observational constraint on that distribution based on this ridge regression model that is learnt from historical reanalysis data. Yeah, that's all I've got to show, so thank you for listening.
Okay, so thank you very much. Well, great. Well, thank you all, because that was a very good session into time. So I think now, if we open up the floor for questions, we have 10 minutes for questions, and also acknowledging that there also may be online questions. So first of all, are there any questions in the room, please? And then we'll go look at the online. Okay, Tim?
Thanks. This is a question for Sarah about the urban heat island. Are you looking only at the annual average of that, or are you taking into account that the urban heat island can be a bit different in the summer and the winter time?
I think you need your microphone.
Yeah, so the plots that I showed were looking at the annual average, but the so the data points on the scatter plot with the observations versus predictions is looking at the monthly averages. So there is different seasonal cycles taken into account in that. Yeah.
Okay. Right. Are there any questions online? Okay. Well, I have a question again.
Robert, there was one from Nam just there.
Okay, please. So I'll just put up with this.
Thanks. It's a question for Sophie. So the microphone can just walk forward 3 layers. And this might be that I completely misunderstood. It was a really good talk. But at the end, I was interested in that result about how the observational constraint basically was pulling those results lower than the CMIP6. So what do you think, is there any risk there in terms of kind of emergent behaviours in the climate system, like shifts or changes in the climate system under climate change that won't be captured by the observational constraint due to the... Does that make sense? Is that there you go. I'll give you that one.
Yeah, so that's actually a similar pattern that we see in quite a few regions. It's perhaps more exaggerated in that region than others, where the top a few kind of most sensitive models are excluded from the observational constraint. We haven't really looked in detail about the cause of that yet. I think when we're looking at the future uncertainty, we've kind of been thinking of it, separating it out into the uncertainty that comes from the changes in the input variables that we're providing from the climate models versus the uncertainty that comes from the relationships that the ridge model has learnt. And one way that we could kind of account more for that, because at the moment we almost assume that the ridge that's learnt from the observations is kind of a perfect model, I guess, and we haven't really accounted for any uncertainty there. So we're looking at using some other reanalysis data sets as well as ERA5 to kind of quantify that uncertainty better, which would potentially shift that distribution up or down, I guess, yeah.
Thank you. Any other questions? Asher, I think the microphone's coming to you.
Thanks. Can I have two? Can I have a clarification from Qianyu, please? Was that river flooding particularly?
Yes, I did. I do the hydrological simulation for each as I shows the catchments in the UK. There are 761 catchments in GB and 28 catchments in the Northern Ireland, but I haven't finished all of them, and in the figure I just show the flooding risks in GB, and still not all the 761 catchments, because the limit of the input data sets, like the NA value or something like that, is around 650 catchments. Yeah.
Okay, great. Yes, because it's just the sort of the overall result of less flooding with climate was less river flooding with climate. So I thought I'd better get that straight in my mind. And Sophie, if I may, really interesting stuff. I know nothing about machine learning, but I was very impressed by the fit of your data and obviously all the work you've done. Could your technique be used for attribution? So, for example, the heat wave of this summer. Here it's still very dry, even though it rained last night. To actually, could machine learning be used to suggest that these extreme events are related to what's going on with climate?
Yeah. So with the historical extreme events, what I'm kind of looking at the moment is using a SHAP value analysis, which basically allows you to quantify exactly how much each of your input variables has contributed to the temperature anomaly prediction in terms of the temperature itself. So that's more looking at, I suppose, whether it's kind of more thermodynamic effects or what's actually contributing to a specific extreme event. And then in terms of the effect of climate change, I'm also wanting to do kind of what I've done with the future constraint on the mean temperature, but look at kind of measures of extremes, so like return values or kind of days above a certain number of days above a certain temperature, and kind of look at the impact of climate in that way.
Any other questions? And has any questions appeared online?
No, nothing online.
Well, I have a question for Sarah, really, which is just, do you think that the kind of understanding that you're developing, maybe I'm jumping ahead of your PhD a little bit, but I'm thinking more about adaptation to heat stress. And I went to Singapore this year, and they're really working it's very sophisticated, looking at how they can reduce the urban heat island effect in Singapore as an adaptation to climate change. And I just wondered, obviously you're using a wider range of methods, simpler methods. Is there any scope with your type of approach to thinking about that kind of question, or is that too far?
Yeah, so I think the kind of like down the line, the benefit of it would actually be in like developing climate-specific solutions to the urban heat island effect. So if the city is in an arid environment, then the measures that you would take to reduce the urban heat island effect will be different to a city in the humid environment. So I think that's kind of mainly how it could be used further down the line. But yeah, I think it's just kind of quite a broad scale thing at the moment, but definitely the climate specific aspect to it could be useful for that kind of adaptation in urban planning.
Okay, thank you. Any other questions?
Nele's still online, so if anyone has a question about the drought but didn't realise they could ask it, I think Nele is still online.
Yes, Nele, I mean, yes, Nele is there. Well, thinking about the machine learning, you know, you're talking about attribution from Asher, and you particularly talked about the event in British Columbia, Western sort of North America. What particular insights did you what insights have you got about that event from machine learning that you wouldn't have got from more traditional analyses, if you follow?
So I haven't actually had a chance to look at that event in a lot of detail yet. I think on the plot that I showed there of the timeline of the event happening, we also looked at how current climate models would have been able to reproduce that event, and that was kind of the dip that was underneath the peak of the ridge regression model. So you could see that they would have under-predicted that event. So I guess the fact that the ridge model is able to so accurately capture it suggests that there's something in there that's not quite being captured by all of the current climate models. So it's just kind of how we interpret that now from the trained model. Yeah.
Okay, so work to be done.
Yes, definitely.
Yeah. Okay. In terms of the hydrological work, with the you mentioned that there are a number of models that were rather poor, and and you excluded those in your analysis, as far as I understood. But I'd like, I mean, what could be done about those areas? Because that was quite a few models, and there seemed to be regional patterns to that problem.
Actually, I didn't exclude them. I still use them, and as I just showed, the NAS value in or the model performance in the UK, and yes, as you said, the catchment in the southeastern of GB is quite low, and I didn't exclude them, although there looks the performance is not very well there, because I think that the catchments there. I talked this with my colleague and my supervisor. I would think that for HBV, those kind of hydrological model is hard for them to simulate properly in those kind of like the groundwater dominated catchments. So I didn't exclude them. I still put them there. Yeah.
Okay, thank you. Okay, please, Phil.
Just a thought here with that last talk, Sophie's one about the model not doing very well in the Western US example or the Western North American example. I wondered whether you were also looking just at temperature with the ridge regression, or were you looking at other variables too? So, for example, we got very hot here this summer, and some of that might have been due to the lack of rainfall as well. So this combined thing of drier and warm, very hot, whether you're picking that up, you need to look at both variables together rather than doing anything independently.
Yes, so the ridge model only predicts the temperature anomaly, but the input variables that I'm using to do that include different relative and specific humidity variables, as well as information about mean sea level pressure and the mean sea level pressure gradient. So the model does have information about the synoptic situation and kind of relative dryness, measures of dryness. But yeah, I guess in terms of looking at impacts of events like that, I'd also want to be considering other factors.
Yeah, it's also whether how long the dry spell has gone on for before the event happens. If it's been really dry for a long period of time, then you get the event. You're going to get the impact that Sarah was talking about with the urban heat island, that you're going to get more of an effect on the city site compared to the wetter natural site. But if the natural site gets really dry, you might get more like the city site then.
Okay, I think that we'll move on now. So if maybe we can just, I think, say a thank you to the students, though, for such a great session.